In this video, we will be talking about work. So, what is work? Well, work is calculated by your dot product between your force vector and your displacement vector, or also known as the magnitude of your, let's just write down with one bar, the magnitude of your force vector times the magnitude of your displacement vector times the cosine of the angle between those two vectors, and this is equal to work. So, what is work? Well, work is sort of a measurement, so to say, of how much your force is actually applying to your displacement. So, for example, you have a box. You have a box, let's say, and this box is being pushed by some force in the same direction as displacement. So, both of these are going directly to the right. Well, that means your force has a positive work. So this is an important thing to know. When your force is going in the same direction as your displacement vector, you're going to have a positive work. So the unit for work is joules. Unit is joules, J. And it can have negative and positive values. And the core unit for joules is kilograms meters squared over seconds squared. And that is because you multiply the force unit times displacement, which is the unit in meters. So this is M. I guess I should, bro, I keep cooking Control X. I guess I should be writing a dot here. This is a M, and this is kg's mass times acceleration. So multiply these two units and you get kg times m squared over second squared. But work is some measurement of how much your force is actually applying to your displacement. What if you have a super small force here? Well, this force is pushing directly to the left in this case, but your displacement is to the right. So if you were to find the dot product of these things, well, your force vector is going directly to the left, your displacement is going directly to the right, so they have an angle of 180 degrees between them. Well, looking at the dot product formula, your cosine value is the only thing that can contribute to negative or positive values. Because your magnitudes are always positive, you can have a negative magnitude. So the cosine is this thing that determines whether your work is going to be negative or positive. So if the cosine, what if the cosine value was cosine of 180, since the angle between the force and the displacement is 180? Well, this is equal to -1. Therefore, your work in this case would be -1, since the force is going the exact opposite direction of your displacement. Now, what if your force, actually, let's not erase that. Let's keep that. So what if your force was straight upward, or straight downward, so to say, and your displacement was straight to the right? So let's say your force is straight upward and displacement was straight to the right. Well, the angle between these two are 90 degrees. Since one goes straight upward, one goes straight to the right, the angle is 90 degrees. So in these scenarios, your cosine value would be equal to the cosine of 90. Therefore, it would just, cosine value would just equal 0. So no matter the magnitude of your force and no matter the magnitude of your displacement, your work will be 0 in this case. So a key point is also, what if they aren't 180 degrees or 90 degrees from each other? What if your force is, let's actually put plus, let's put plus force here. This is negative work, and this is 0 work. This is 0 work. Now, what if your force is, so to say, at an angle? At an angle, and your displacement is straight to the right in this case. Well, if your force is at an angle greater than 90 degrees, then the cosine value will always be negative. So if you take in trig, as long as theta is greater than 90 for cosine, 90 degrees for cosine, then cosine will be negative. Let's put negative here. Cosine will be negative. And as long as theta, right? So let's draw another box. So as long as theta is, so you know what? Maybe I should draw the force and displacement vectors first. So this is straight to the right. The force is kind of at an acute angle with the displacement vector. So as long as theta is less than 90 degrees, then your cosine value will be positive. So as long as your force vector creates an acute angle with your displacement vector, then you will have a positive. So as long as force creates an acute angle with your displacement, you'll have a positive work. So this positive work. If it creates an obtuse angle, it will have a negative work. If it creates a right angle, you're going to have a work of 0. And if it's going directly in the same direction, well, it's technically 0 degrees. But for our sake, 0 degrees could be, I guess, considered as the same as acute. It's not acute, but since their force and displacement vector are going in the exact same direction, your work will be positive. And if it goes in the exact opposite direction, it forms a 180 degree angle. So if your force and displacement forms a 180 degree angle, then your work will be negative due to the fact of the cosine. So you can always think of the cosine here. That changes your work's positive or negative values. So just to add a little bit of nuance for the you calculus folks that calculate work, work can also be expressed as an integral. So it can be expressed as the integral of your force. This is for varying forces if your force isn't constant. So if your force is some function, dotted with your displacement. And if you've taken vector calculus, this is something that might terrify you. But overall, you likely won't need to use this for your mechanics class. I didn't have to, at least. But I just wanted to cover that. Also, another quick thing to mention, work is equal to change in kinetic energy. And that's an important thing that you're going to learn. So if your kinetic energy doesn't change, then your work is equal to 0 as well. And I'm going to have a video on that because work and kinetic energy are very, very much tied together. So the video, I'll put it down, the link in the description, but it's going to be called the work energy theorem. And it's just going to combine kinetic energy and work together. So we'll start off with a very, very simple problem. It's just one direction. There's no angle between the vectors. They're pointing straight in the same direction. So how much work does a supermarket checkout attendant do on a can of soup as he pushes it horizontally with a force of 5 newtons? So horizontally, both left or right. It didn't mention that they're going in different directions. So let's just assume this guy's pushing it to the right. So we have a can of soup. Let's try to draw the can of soup. It's the can of soup. And he pushed it. So the checkout attendant pushed it 0.6 meters to the right and pushed it with a force of 5 newtons as well. So I guess the vector lengths don't really matter that much in this case, but let's just draw the vectors with the same length. This one technically should be shorter since the magnitude is shorter, but don't worry too much about that. And remember that the formula for work is just equal to, so work is equal to the dot product between force, which is just also equal to magnitude of force times magnitude of displacement times the cosine of the angle between the two vectors. So since these two vectors are going in the same direction, cosine of 0 occurs, not cosine of theta. Cosine of 0 occurs because the angle between them is 0. They're both going in the exact same direction. So our entire formula here for work is just equal to force times magnitude of force times magnitude of displacement. And we already given that. So the magnitude of force is just equal to 5 newtons times the magnitude of displacement, which is just 0.6 meters. Let's use green there, actually. Times 0.6 meters. Therefore, work is equal to 3 joules. So again, work is the unit of joules. I also have to mention that I get these problems off OpenStax. Link in the description. Online textbook. Practice problems. They're very good. But let's go on with the problem. How much work is done by the boy pulling his sister 30 meters in a wagon as shown below? Well, looks like this boy had a displacement of 30 meters directly to the right. But the force that he's exerting on this wagon is kind of at an upward angle. So remember, work is calculated by the dot product between force and displacement, which is also the magnitude of force times the magnitude of displacement times the cosine of the angle between them. So right here, we have the force of 50 newtons. So we can plug this in, 50 newtons times our displacement magnitude, which is 30 meters. It's kind of blurry. I don't know if you can see it. Okay, I'm not writing this m right. Times the cosine of the angle between them. And the angle between them is given. It's 30 degrees. Since the force is 30 degrees from the horizontal and displacement is going straight to the horizontal, your force vector is 30 degrees from your displacement. So once you multiply all these together, 50 times 30 times the cosine of 30, you get a work of 1299.04 joules. So these are pretty simple one-step problems, but we're going to go on to some that maybe might take more thinking. As I've said, now the problems are more complicated. A shopper pushes a grocery cart 20 meters at a constant speed on level ground. So, constant speed. Key point, constant speed. Underline that. Underline. Okay. Against a frictional force of 35 newtons. So, friction, usually negative. It will resist movement. So, when you're moving somewhere, friction is going to go the opposite direction, usually. So, you can already assume the work done by friction is negative. He pushes it in a direction of 25 degrees below the horizontal. So, let's try to draw the shopping cart and mark down what he's talking about. Okay, that's the handle. And these are the wheels. And this is the shopping cart. Let's see this. So, shopper pushes a grocery cart 20 meters at a constant speed. You know what? It'd make more sense if the shopping cart was, the handle was in the other direction, actually. So, right here. So, this is a target shopping cart because the handle's red. So, he pushes in a direction of 25 degrees below the horizontal. Key point, underline it. 25 degrees below the horizontal. Against a 35 Newton frictional force. What is the work done on the cart by friction? Well, friction is going to resist movement. And the question states that shopper pushes grocery cart 20 meters. So let's assume 20 meters to the right. But friction is going to resist movement. So friction moved at friction's force is 35 newtons. So on level ground just means that these two, well, displacement means it's straight to the right due to the level ground, and friction is straight to the left since it will resist any movement. So let's solve for the work due to friction. Part A, work due to friction. Work is the magnitude of their force, displacement, times the cosine of the angle between them. So, magnitude of force here is 35 newtons. The magnitude of your displacement is 20 meters. And the angle between them is 180 degrees since they go in the exact opposite direction. So the cosine of 180 is here. Well, when you multiply all these together, you get 35 times 20 times, well, negative 1, because cosine of 180 is equal to, this is equal to negative 1. Maybe that's a little unclear due to all my, I'll just put negative 1 down here. And when you multiply all these together, you get a work of negative 700 joules due to friction. So that makes sense. Friction is normally going to be negative. Maybe an exception for those people that are curious. Probably when in centripetal systems. So the centripetal force caused by friction by a car driving around a curve, that's going to have a work of, well, actually depends on what you're comparing it to. It could have a work of 0. I don't know. Okay. That doesn't matter. That's completely besides the point. Let's solve for B. Well, what's the work done by the cart by gravitational force? Solve for B right here. Well, gravitational force straight down. mg. We're not given the mass. We know this is Earth, so gravity is 9.8 meters per second squared. But we're not given the mass of the cart. But that completely doesn't matter, because no matter what the weight force is, the angle between the weight force and your displacement is 90 degrees. One is straight down, one is straight to the right. So the angle between them is 90 degrees. If this was R and this is the weight force. Weight. So, with the work formula, you would get the, let's rewrite it. You would get that the angle between them is the cosine of 90. And cosine of 90 is just equal to 0. So no matter what any of this is, when it's multiplied by 0, all turns to 0. Therefore, work caused by gravity is equal to 0 joules. So I'm going to write the answers up here. Negative 700 joules, because I need to free up some space. B is 0 joules. Okay, let's erase. Let's get some real estate now. Okay, let's do C. What is the work done? What is the work done on the cart shopper? By the shopper. So, remember, this shopper is pushing at a 25 degree below the horizontal. So if they're pushing on the handle, this is kind of what the force would look like. 25 degrees below the horizontal. So horizontal is parallel to the floor, and you'll have a 25 degree angle here. So now that we have the angle of the force, how do we find the push force, angle of the push force between the horizontal? How do we find the magnitude of this push force? It's not given in the problem. Little Johnny, it's not given in the problem. How do you solve it? Well, a key thing that is part of, wait, there's dust here on my mouse pad. A key thing that is important in this that I underlined before is the constant speed. Since the speed is constant, there's no acceleration. Therefore, the horizontal component of your push force must equal your frictional force. So let's write that down. So this is the magnitude of your force, F. But to find the horizontal component, you just multiply it by the cosine of 25. And this should equal 35 newtons. Because this horizontal component of your force, so F of x, must equal your frictional force due to the constant speed. So change in velocity. This is because change in velocity is 0 meters per second. So we can divide both sides by the cosine of 25, and you will get a force of 38.62 newtons as your magnitude of force. So now that you have the magnitude of the force, you can solve for the work done. So what is the work done on the cart by the shopper? Well, work is equal to magnitude, let's draw that bigger. Work is equal to magnitude of force times displacement times cosine of, cosine of theta. So we have the force now. The magnitude of our force is 38.62 newtons. The magnitude of displacement is just simply 20 meters. And the angle between the force and the displacement is, well, 25. Since the displacement is also horizontal and the force, our push force, is 25 degrees below the horizontal, the angle between them is simply 25. So if you solve for the work here, you just get, oh my god, my callus. Ow. So while I'm typing this in the calculator, I'm just going to tell you the reason why I just said I hurt my callus is because I just did a triple PR in deadlift. I know you guys don't care. I'm just talking to talk. But you're going to get approximately a work of 700.03 joules. But let's just approximate this to 700 joules. So answer for part C is 700 joules. That is the work done by the cart on the shopper. Now, if you didn't do any rounding in the middle of this equation, you would have gotten exactly 700. Okay, how about this? Find the force the shopper exerts using energy considerations. So let's clear this up. Find the force the shopper exerts using energy considerations. What in the world? We just solved for it. What was it? 38 something? I'll just say 38 newtons. Actually, I'll just click on do. 38.62 newtons. Boom. This is part D. So as you solve for part D, you solved for as you solve for part C, you solve for part D. Oops, I forgot to finish the J here. Last part. This is something that you haven't learned yet, part E, something you have not learned yet. But what is the total work done on the cart? I'll try to explain it. So if you know what kinetic energy is, per the work energy theorem, work is equal to change in kinetic energy. So since this cart stayed at a constant speed, the kinetic energy didn't change at all, due to the fact that kinetic energy is dictated by speed. So kinetic energy is dictated by speed. And since you're staying at the constant speed, well, your kinetic energy changed by 0, therefore your work changed by 0 joules. So what is the total work done on this cart? You didn't even need to calculate anything to solve for that. But if you were to add both the work of the friction and the work of the push force onto the displacement, well, you would get 700 joules plus negative 700 joules, sorry, plus 700 joules. This is just equals 0 joules. So your work done is in total 0. All right, last question. Oh my God, finally, computer engineering Jitty, which is a username that I should probably change. Finally, the last question. I just took a break. I ate dinner. My mom brought home some food. It was nice. Corner Bakery, amazing food. Shout out to them for very good sandwiches. We got a chicken sandwich with a bag of chips for $3. Yeah, sometimes a bag of chips cost $3 themselves. We got entire chicken sandwich with it. It was pretty good, actually. It was actually pretty good. Let's get into the problem now that I am full and I am energized. Okay, so 5 kilogram box pressed on a horizontal surface. Coefficient of kinetic friction between the box and the surface is 0.5. Underline that. Important information. 5 kilos, important information. Constant velocity, always important information. And your displacement, or the horizontal movement, is just 10 centimeters. So, R has to equal the unit of meters. Well, 10 centimeters just equals 0.1 meters. So, now we have our proper unit here. So, let's solve part A. So, part A, the applied horizontal force. So, find the work done by the applied horizontal force. Well, due to the constant velocity, your frictional force, your kinetic friction, and your applied force, let's say applied force, is equal to each other. There is no acceleration, therefore the velocity is constant. So your friction force and your applied force are the same. So now, what do? Well, let's solve for the part A. Well, I guess if you solve for part A, you solve for part B. So, part A. Let's solve for, I guess you have to kind of actually, you kind of have to skip steps. You kind of have to solve for the frictional force because you can't solve for the applied force without solving for the frictional force. So, let's solve for part B first. Your weight, let's say WE, weight is equal to mass times gravity, because in order to solve for frictional force, we need to solve for normal force first. So let's multiply our mass. So 5 kilos times 9.8 meters per second squared. Type that into my calculator, and then I get 49 newtons. So that's our normal force. And in order to find our frictional force, we just need to multiply our coefficient of kinetic friction by the normal force to get your frictional force. So we have our normal force here, 49 newtons, and we have our coefficient of kinetic friction, 0.5. Therefore, the frictional force is 24.5 newtons. So if our frictional force is 25.4 newtons, frictional kinetic force, then that means our applied force is also equal to your frictional force due to the constant velocity. So now that we found both of the forces, we can calculate the work done by each of them. Well, work is calculated by force, magnitude of force. I'm going to start writing the bars now, times the magnitude of displacement times the cosine of the angle between them. But in this case, your push force isn't at an angle. It's going in the same direction. So where to say that? Horizontal pull force, actually, it's a pull force, goes in the same direction as your displacement. Horizontal force pulls the box for 10 centimeters, so it's going in the same direction, and friction is going in the opposite direction, so that will have a negative force. So let's draw the box right here. This is your box, 5 kilos. Your force of pull, I guess the applied force in this case, is in the same direction as your displacement, r. And your friction force goes in the opposite direction with equal magnitude, as we already determined that before. So F of K, your kinetic friction. So to calculate the work, we need to multiply force times displacement times cosine of the angle between them. So the work for the pull force is equal to 24.5 newtons as our established pull force, times displacement, which is 0.1 meters, times the cosine of the angle between them. And since they point in the exact same direction, the angle between them is 0. So this just equals 24.5 times 0.1, which is equal to, so 24.5 newtons times 0.1 meters, since the cosine of 0 is just equal to 1. This is just equal to 1. Multiply these two together, you just get 2.45 joules. And for the friction force, and let's write down, this is the work for pull. This is, okay, bad arrow, W, pull. But for the work for friction, well, I can already predict it's just going to be 2.45, but negative. But let's go solve for it. So work for friction is equal to 24.5 newtons times 0.1 meters. So the magnitude of your friction force is 4.5 newtons as well, as we established in part A and B. Our displacement is just, this is not a decimal, it's just a times, dot for the time symbol. Our displacement is 0.1 meters. And the angle between them, since they go in the exact opposite direction, the angle between them is 180 degrees. The angle between the friction and the displacement. I should stop saying it. I feel like it is a not good word to use when you're teaching. I should stop using that. So multiply all this together, well, you just get 24.5 newtons times 0.1 meters times, well, negative 1, since the cosine of 180 is equal to negative 1. So, well, we already established 24.5 times 0.1, and that multiplied by negative 1 is just equal to negative 2.45 joules. As both the work for, let's use green here, because green means that we finished the problem, as the work for our frictional force and the applied horizontal force. And the net force in total, well, it's 0 due to the constant velocity. We didn't even need to answer the other problems. The net force is equal to 0 newtons for part C. So, as always, if you have any questions, put it down in the comment section. I hope this video helped.